SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are back again to this course Applied Thermodynamics, Module 4 Gas Turbine Engines. Previously, we have covered 5 lectures on this topic, that is Module 4 Gas Turbine Engines, and we are discussing in the last class about the aircraft propulsion cycle part 1. Now, we are in the last lecture of this module, that is aircraft lecture part 2. Of course, in the aircraft propulsion category we have covered most of the things, but here we will put same concept but in a different context. So, the main intention of this particular lecture is based on some concepts like jet propulsion, ramjet propulsion, and we will also discuss about efficiency of turbojet engines, and in fact we are going to calculate the pressure thrust on a turbojet engines, and to some extent we will cover about the combustion process in a gas turbine engines. So, previously in our last lecture we discussed about the a jet engine, it is divided into two broad categories, that is one is turbojet engine, other is turboprop engines. So, in a turbojet engine the thrust is developed through a propelling nozzle, we call this as a jet, and in a turboprop engine majority of the thrust is developed through propeller, and air passes through the propeller and gives the forward thrust as and when it goes out from the engine. Now, over the period of time there are many developments in the propulsion engines, such as we have piston engines, we have turboprop engines, we have turbojet engines, turbofan engines, ramjet engine, scramjet engines. And if you want to travel faster, then we have to change the propulsion engine in this order. So, for example, for subsonic aircraft we can achieve it through a turboprop engines or turbojet engines, but if you want to go for supersonic engines, then you have to use ramjet engines, it is operated in a different concept, and further if you want to travel at hypersonic speeds, then we have to use this scramjet engines. But in a thermodynamic sense, we call this aircraft propulsion as a device, and which is nothing but a heat engine that drives the propeller, or by allowing high energy fluid to expand and leave the aircraft in the rearward direction as a high velocity jet. But this is what happens in a turbojet engines, and in a turboprop engines there are large log of masses that enters through the from the front end, that is through the propeller, and this gives the necessary thrust, and for which the moderate velocity is achieved in the backward directions relative to the aircrafts. So, in a turbojet engine the aircraft induces comparatively small airflow and gives high velocity jet backward to the relative to the aircraft. But whatever you call this as a turboprop or turbojet engine, in the very fundamental principle that remains hold good, that is the Newton's law, which means that rate of change of momentum of air provides reactive thrust to propel the aircraft. Now, let us do a very simple analysis in which whether it is a propeller or jet engine, for which there is a velocity of the jet which is defined as Cj and the velocity of the aircraft which is Ca. So, you can see here the Cj is your jet velocity, whereas aircraft velocity is Ca, and similarly same thing happens here also for turboprop engines. And when the jet expands, it expands to atmospheric pressure, and then there is no thrust due to pressure force, since it has already expanded to atmospheric pressure. But if you do not expand it to atmospheric pressure, then we will have a pressure thrust. So, in order to keep the aircraft moving at a constant velocity, and typically this is what we call as a cruise velocity at high altitude, the thrust equivalent work must be provided to overcome the frictional resistance and drag. So, basically the net work output from the engine is given by increase in the kinetic energy, that is through the jet, and it is used in two ways. First one, it provides the thrust work, because this kinetic energy provides the thrust work, and also it imparts the kinetic energy which to the air which was initially at rest, so that it receives absolute velocity Cj minus Ca. So, initially it was Ca was 0, but as and when the kinetic energy of the jet is imparted, the relative component of Ca and Cj keeps changing. So, in a sense that we can define the propulsive efficiency, which we have already defined in our last class by analyzing the entire thing as a propulsive duct. Now, we are going to apply the same concept for a turbojet and turboprop engines, but the concept remains same. So, it is the propulsive efficiency is defined as the ratio of thrust work to the rate at which work is done on the air in the aircraft. From this, a simple relations can be made that thrust power per unit mass flow rate, that is F is equal to Ca times Cj minus Ca, so that work output from the engine becomes W, that is nothing but half Cj square minus Ca square. So, you can say propulsive efficiency, this can be defined by twice Ta by Cj plus Ca. Okay. Now, one interesting thing that we can see here, that the propulsive efficiency increases with aircraft velocity. Okay. So, with increase in the aircraft velocity, the propulsive efficiency increases. But one interesting thing is that if you analyze it for a propeller driven aircraft, which is turboprop, or a jet engine aircraft which is turbojet, some interesting features can be seen. What you can see is that in the beginning of period of, means when you keep on increasing the aircraft velocity, you find that propeller gives a better approach, means better propeller efficiency. The propulsion efficiency is high as compared to jet. But what happens at one particular time, maybe about 700 or 800 kilometers per hour, somewhere here maybe about 600 kilometer per hour, this propulsive efficiency drops. So, when the propulsive efficiency drops, then but in contrast, when if you say jet engine, its propulsive efficiency keeps on increasing with the aircraft speed. So, means that at one particular instant or time, the jet engines takes the advantage of a propeller engines. So, when normally you might have seen when all the commercial aircraft, when they are supposed to run at lower speed, they prefer to have a propeller driven machine or engine. So, we call as a propeller engine. When they when we have a, when the jet, when they go for a very high velocity at the at high altitude, then turbojet or turbofan engines are preferred. And this remarkable change that we say that jet engines becomes more efficient when the Mach number is about 0.7, or when we expect the flight velocity to be more than 850 kilometer per hour. The another concept that drops in from this jet is the what we call as a ramjet engine. So, the ramjet engine, what happens? So, it is simply we call this as a ramjet engine, in which the compressed air is used for conversion of kinetic energy of atmospheric air relative to the aircraft, and we call this as a ram effect. So, so what happens? You can say in ramjet engines, the air inlet that comes from the station 1, and finally it goes at station 2. So, through this process, this duct, the inlet acts as a intake, and it acts as a diffuser, that means the flow velocity decreases. So, the intake of ramjet engine acts as a diffuser, and the kinetic energy of the air is used for the stagnation temperature rise after this diffusion process. Other concepts that are used here, that air attains the stagnation pressure when the process is isentropic, while for irreversible adiabatic, and in fact this duct is typically an adiabatic duct, the air receives less pressure than the stagnation value. But whatever the case may be, the stagnation temperature does not change, that is 1 and 2, the stagnation temperature does not change. The other concept of ram propulsion is that when the aircraft is powered by a ramjet engine, it requires auxiliary power supply to attain this velocity, which is necessary for starting of the engine through ram compression. The idea of ram propulsion drops in when you are supposed to attain supersonic speed, but in order to reach this supersonic speed, we cannot go in a single instance. So, what we have to do? We have to go to first thing, we have to go to certain altitude where you have to cruise at the supersonic velocity. But to go to that altitude, we require some other means of propulsion system, which we call as auxiliary power supply. So, it could be a conventional turbojet engine or turboprop engines, and finally, we have to fire these ramjet engines, for which the propulsion is achieved through this high velocity duct. So, means that is what he says, that we require, for the starting of the engine, we require additional power unit and unit to attain the air velocity, that is at the inlet. The other thermodynamic aspects are the total pressure. The total pressure is achieved by the air when the diffusion process is isentropic, and if it is irreversible, the total pressure will be less than the isentropic value. And of course, the available kinetic energy remains the same irrespective of the process, because the temperature remains the same. So, a brief calculations in this aspect we can have here is that the thrust power per unit mass flow rate, which you can calculate, F is equal to C A times C j minus C A. So, from this we can get also work output from the engine, that is half C j square minus C A square. So, based on this we define this propulsive efficiency. Now, considering this flow to be isentropic flow, we can write the equations, and looking at the TH diagram, we can write Cp times T1, that is the total pressure energy, is nothing but the static pressure Cp times T1 plus half Ca square. So, from this we will get a temperature difference, total temperature difference at station 1, and that is nothing but Ca square by twice Cp. So, based on the, since the process is isentropic, other relations between stagnation pressure and static pressure will hold good. And of course, we said that the total temperature at T02 and T01 remains same, because there is no extra heat is added into this system. And based on this, since it is acts as an intake, we can write the intake efficiency by through the temperature drop, that is T02S minus T01 divided by T02 minus T01. T02 minus T1, and this typically it is simply the ambient temperature or pressure. So, this is all about the ram propulsion when you want to go travel faster. Apart from this, let me discuss some other thermodynamic aspects that we typically define for isentropic efficiency and with respect to a turbojet engine. So, in earlier situations, when we define this as efficiency, we normally do not encounter or do not take into account about the kinetic energy or potential energy change in our temperature or pressure calculations. But when we are going for aircraft engines and that too in turbojet engines, it is not advisable to use those static value, rather we prefer to use the stagnation values, because implicitly the kinetic energy changes are already taken into account while calculating the stagnation temperatures or pressures. Now, let us see this typical TS diagram in which we have plotted different pressure changes that happens, and what has been plotted is that when you start the process, that is maybe you start at 0 pressure, here 0 stands for P naught, that is nothing but your ambient PA or TA. So, as if we are traveling at altitude maybe 10 kilometer above the earth surface, and at that point whatever ambient pressure and temperature conditions they are, that point of time the air is stagnant. So, the static value and stagnation values remain same. So, this is what it starts, and from this 0 to 1 process is your intake process, and through this intake process, had the process been isentropic, it would have gone from 0 to 1s, but now it goes to 1. Now, from 1 to 2 it is a compression process, and if it in isentropic compression, then it would have gone to from 1 to 2s. So, here we look for these are the static P1 and P2 value, and corresponding stagnation values can be also calculated. Now, from 2 to 3, and if you see the process 2 to 3 is in a heat exchanger process, or in our case we call it as a combustion chamber. So, in a combustion chamber some kind of pressure drop is always ensured. So, this pressure drop is taken into account as delta pressure delta P, that is in the combustion chamber, that because of which the whatever pressure that enters into the turbine at state 3, it is not at the compressor outlet pressures. So, there is a typical drop in this pressure. So, we say that at state 3 air enters to the turbine, and from the expansion process takes in 2 steps, one in the turbine. If it is in the turbine and the process is isentropic, then it will go as a 3 or 3 to 4s, and if it is a real process, so it will go as a 3 to 4. And from 4 the process that happens is in the nozzle, because the expansion takes place in the nozzle to generate the thrust. So, had the process been isentropic, then it would have been 4 to 5 s, but actually it should be 4 to 5. Now, here the typical conditions that when this expansion takes place, that point of time whatever type of nozzle people use or in the engines they use, typically nozzle becomes choked. That means that is the optimum flow rate or optimum thrust that can be achieved from the nozzles. So, normally condition 5 and 5s, they are almost the above the ambient value, and the flow condition is typically to be choked, and in fact pipe and atmospheric are not equal. So, the all entire calculations are governed through the choking condition of the nozzle. And when you talk about efficiencies, we have 4 efficiencies that comes into picture, one for intake duct, other for compressor, third for turbine, and 4 for jet pipe, or we can simply say propelling nozzle. So, in a similar sense, the efficiencies are defined based on their ratios of actual value and isentropic values. Now, moving further, we are going to discuss on the pressure thrust on a turbojet engines. In fact, in previous lecture we discussed this pressure thrust, and that concept was typically different in a sense that there we defined three pressure ratios, one is nozzle pressure ratio, one is ram pressure ratio, and we found out a non-dimensional thrust coefficients, and we through as a function of nozzle pressure ratio. So, as a layman, if you want to go for a change in the thrust coefficient, we can simply change the nozzle pressure ratio, but that was a different context in which pressure thrust was calculated. But here we will use some similar concept, but our approach will be something different, and let us see that how we are going to analyze here the pressure thrust calculations, and again we will stick to our simple engine, that is turbojet engine. So, very basic philosophy that the gas expands to ambient pressure in a jet nozzle, but the back pressure is always lower than the pressure at the nozzle outlet. So, this phenomena is called as under expansions. That means, it could have expanded, but this our system or your pressure difference does not allow. And due to this pressure difference, in addition to this your momentum thrust, the aircraft also experiences additional thrust, which is known as pressure thrust. So, we are going to consider this pressure thrust, and for this we take care about a turbojet engines, in which their intake has a certain area A1, that is intake locations, and the exit nozzle exit area, that is flow comes out from A2, and it is at pressure P2. And based on this, and when the aircraft is and also what we can see, jet velocity is Cj, which is in this direction, and your aircraft velocity is Ca in the forward directions. And when the aircraft is cruising, your thrust is total thrust that acts is equal to the drag, because they have to balance, and so that it will keep the aircraft always in the moving conditions. And in another view, that is frontal view, you can say the outline area, and this particular area we can say, actually this particular area you call this as a aircraft outline area. And in fact, although the aircraft are a lot of big area, that enclosure big area that we have, but for our thrust calculations it is taken with some outline area, and that is decided at which the engine is located. And from this we can use the Newton's law, which says that net force is nothing but rate of change of momentum of working fluid in the direction of motion of the fluid. So, let us do this calculations, that from the Newton's law we can say how much force that acts on the aircraft, that is through the jet, and from the pressure force, and that is nothing but your reaction force. So, the net force becomes R reaction force minus drag and plus this pressure with respect to this area, aircraft outline area. So, from this we get an expression for drag, which is nothing but d is equal to R plus Pa into A1 minus A2. Now, when thrust equal to drag, so that we can write T is equal to this particular one, thrust is equal to drag, then we can write this particular expression as this. So, that by putting D in this equation we can calculate the total thrust. And if you look at this particular equations, the total thrust composed of three parts. One is through this jet, other is with respect to area A2, what is the pressure difference, that is P2 minus Pa, and with respect to area A1, what is the pressure difference, that is P1 minus Pa. So, where Pa is your ambient pressure. And for a subsonic aircraft, I think the second term does not appear, because there is some different concept that drops in, that is through formation of, there is no shock waves into pictures. So, that this particular term does not appear for the subsonic aircraft, but for the supersonic aircraft the entire flow which is outside this medium also gets disturbed. So, because of this reason this particular term remains. And the other concept that in the pressure thrust calculation in the turbojet engines has some salient features. What are they? So, at least sea level conditions with same exit area of the propulsion nozzle, the thrust produced is higher than the mass flow rate through the unit. Because since the mass flow rate of the unit is increased, the thrust produced will be higher. That means, at sea level conditions your thrust will be higher, because the mass flow rate into the unit is increased, because at the sea level conditions your density is high, means that is at the atmospheric density, but at higher altitude your density is less. So, mass flow rate is also, that is entering, is also less. So, at higher altitude it is always preferred to use a variable type nozzle, and typically this variable area nozzle is nothing but a convergent divergent nozzle or simply a under expanded convergent nozzle. And based on this, when we say that nozzle is choked, and all our calculations are normally driven through the choking flow conditions of the nozzle, and in fact the choking flow calculations is very simple relations. In many aircrafts people think about of thrust boosting. So, whatever you calculated, that we say momentum thrust or pressure thrust, that is based on the whatever flow jet velocity and what is the ambient pressure and what pressure we are operating. So, all these things that we get, there is a fixed amount of thrust that is involved, whether it is as a cruising stage or takeoff stage or landing stage. So, in all three cases we can calculate the thrust. But what happens in some situations, we expect to travel faster while cruising. So, in some cases people prefer the method what we call as a thrust boosting, and this thrust boosting is normally achieved through afterburning. Afterburning is nothing but simply we call this as a reheat. So, when you deal with the reheat cycle of gas turbine, we say that the heat is added separately and to reach the maximum temperature, and the gas after the reheating further expanded in another turbine. But here we do not we do add heat, and while doing this heat, and in this process, this instead of calling this as a reheat, we call this as a afterburning, and fuel is burnt separately in another method, and we call this as a afterburning, or an afterburner is used, or you can say it is a secondary type of combustion chamber. And the secondary combustion chamber, the fuel is spread into the gases which leaves from the turbine, thus it increases the jet velocity. And through this afterburning concept, there is a possibility that we can increase the thrust by about 50% higher, but at the cost of extra fuel. And in aircraft terminology, the cost of extra fuel means it is a very costly affair. So, it may not be economically viable for going for afterburning unless and until it is really required. So, the afterburnings are normally incorporated during the starting, where we require higher initial thrust or as a reserve power source for thrust augmentations. So, at the time of need, and in fact whenever this afterburner is used, it is used for a very short period. We just switch on for maybe for few minutes, and then we switch off the burner. And apart from this thrust boosting, people used the other variant of aircraft engines, and we call this as a fan engine or bypass engines. So, in fact, when the air comes enters to the engine, so whether we say turboprop or turbojet engines, so and all this air that comes, we call this as a primary air. But the other variants, I mean, to improve this efficiency of this airflow, people have used the concept as a ducted fan or bypass engines. That means, out of this total air that enters, some of the air, majority of the air goes as a primary air, other quantity of air we call as a secondary air. So, through that managing this airflow will be better, and through this we can also get a better approach in running this afterburner. So, in some cases the bypass air is directly goes as a afterburner, either it can be used as a afterburning of the fuel, or it can use and give an additional thrust which if in goes without burning as well. So, that comes in a separate aspect, and all these things are covered in the aircraft propulsions. And in fact, in our course we only deal with the thermodynamic aspects of this propulsion system. And the last segment of this aircraft propulsion, or in fact in gas turbine engines, is combustions. And we have more or less we have covered all the components: turbine, compressor, main intake, nozzle, all these components are covered, but we have not discussed anything on the how the combustion process happens in the gas turbine engines. So, irrespective of the fact that whether you use this engine, the combustion process in a conventional gas turbine engine or in a jet engine, the more or less the mechanism of combustion remains same. Another point I need to emphasize, that when you deal with the gas turbine combustion and if you try to compare IC engine combustions, both are a little bit different, and here because IC engines it can operate as a constant pressure mode or constant volume mode, whereas in a gas turbine engine it is always operated at a constant pressure based combustion, number one. Number two, that another difference that we can have here, that when you deal with the combustion in IC engines, these are cyclic in nature. So, that means it in a continuous cycle combustion takes place only for certain duration of crank rotation in IC engines. But here in the gas turbine engines it is always a continuous combustion. Now, when a continuous combustion is used, so side by side we also expect that we have sufficient level of turbulence, there should be proper mixing of air fuel, and another important aspect is that here the air velocity is very fast, and because as and when your speed also increases, air velocity also increases, air velocity is very fast, and mixing is another criteria, proper mixing is another criteria for of importance for gas turbine engine combustions. So, for that different types of mechanism that has been used, that instead of sending the air that means outlet from the combustion chamber, it has been proposed that a series of air outlets are sent in a air does not go as a single slug, it goes as a multiple slugs at different outlet points from the compressors. So, that is what we call this as a combustion process in the gas turbine engine is different. So, if you look at the particular figure here, whatever I have discussed, if I just explain with respect to this figure, we can say that in the inlet the air comes from the compressors, and after the combustion process is over, the combustible gases goes to the turbine for expansion. But in this process what happens, now when air enters to the combustion chamber, there are possible ways of entering. That air can come through different bypass region, other it can come, and we call this as a primary air. So, means majority of the air comes as a primary air. Other type of air that comes through the, that means if you take this is as a cross section, and in the circumference we have holes, we call this as a dilution holes, and in this dilution holes also secondary air also comes in. Now, when the primary air goes in, it encounters the fuel injection process, and this fuel injection process is nothing but typically whatever you do in the constant pressure based combustion in IC engine, in CI engine. And here additional devices, that means fuel goes as a spray, goes as a spray through fuel nozzle, and also we have swirling vanes. So, it gives a proper mixing of this primary air with this fuel. So, the flame plant gets generated and it tries to propagate. But with time, and if you look at, this is a fuel rich zone because the entire fuel is sees this air, and as and when it as and when the flame goes, it gets additional air through this dilution hole. So, in a process what happens, by this means the flame gets stabilized, so that we get a sustained flame throughout this combustion chamber. And when we have a sustained flame, that means we can ensure that combustion efficiency is very high, and means all the fuels gets combusted. So, this is how we and finally, at the end of the towards the end of this combustion chamber, the combustible gases goes to the turbine. So, this is how, and this particular arrangement we call this as a can type based things, where the air leaving from the compressor is split into the several streams and it is supplied to the combustion chamber. Of course, initially the combustion is initiated electrically, and when the fuel starts burning, the flame is stabilized in the chamber. And some of the air from the compressor is introduced directly. So, we call this as a primary air, and it is only about 25% of the total air. The remaining air enters to the annulus or through these dilution holes, and in the flame tube, the primary air forms the rich mixtures and temperature is high in this zone. So, while entering the air entering the dilution zone completes the combustion, and it helps to stabilize the flame in the high temperature zone. And if you give some typical numbers for this, the air fuel ratio in a gas turbine engines is 60 to 120. Remember, whereas in our IC engines it is 14.5, that is stoichiometric air fuel ratio, but here it is 60 to 120. And air velocity at the entry of the combustion chamber is limited with 75 meter per second, because if we keep on increasing the air speed, we do not have sufficient mixing time. So, it is so to the best available technology till today, we say that the air entry to the air velocity at the entry to the combustion chamber is limited by 75 meter per second. And of course, in a similar context, when you deal with rich and weak limits in the IC engines, we call either rich mixture or lean mixture, and it leads to a condition if you do not, and there are possibilities of knocking. Similar case also happens here in the gas turbine engines, and this particular phenomena we also call as a screech. So, screech is nothing but a situation what we call as a combustion instability, and similar terminology that we use in the IC engine is nothing but knock. And when this screech phenomena, that means we always ensure that knock should be avoided in IC engine combustions. So, in some cases we should avoid this particular phenomena screech in the gas turbine combustions. And in some such situations, the gas turbine engines use afterburners. So, this is similar to the concept called as reheating, and this reheating is performed between turbine stages or after burning of the fuel is usage for satisfactory usage of additional fuel requirement. That means, all of a sudden we do not use this fuel directly in the primary combustion chamber, rather fuel path is outlined in such a way that as and when is required, fuel can be supplied to the afterburner to satisfy the requirement of additional need. And of course, there are some pressure losses we have been keep on telling in our analysis, and this pressure loss is mainly due to non-adiabatic flow, turbulence and frictions. And there is a continuous pressure loss, but what happens at a given cross sections, typically the pressure is constant. At a given cross section of gas turbine in the combustion chamber, pressure may be treated as a almost constant. And in combustion torn, the pressure loss which happens due to friction is called as a cold loss, and the pressure loss that happens due to heating process we call as a fundamental loss. And more or less what you can say, pressure loss is inevitable. And there are some terms like combustion efficiency and combustion intensity. So, combustion efficiency we have been utilizing many aspects that in our many problems. It is nothing but for a given temperature rise, the combustion efficiency is nothing, we can define it as a theoretical air pressure ratio to the actual air pressure ratio. And to calculate this theoretical pressure air ratio, we can plot this combustion pressure rise and fuel air ratio for given air inlet temperatures. This is how we use this graphical approach. A concrete picture of gas turbine theory from the book, it has been shown that a graphical approach is very widely used. What it tells is that in a x axis the fuel air ratio is plotted, and the y axis means same concept, that is here it is a combustion temperature rise also plotted in this case in the y axis. And for a given air inlet temperatures, these are the lines which are drawn here. And as a user, what you require, what your expectation, that you have to use this particular graph to calculate the fuel air ratio. Now, to calculate this fuel air ratio, you need two parameters. One is the combustion temperature rise, other is the air inlet temperatures. And the combustion temperature rise can be calculated by knowing the temperature or stagnation temperature differences between the across the combustion chamber, or it is nothing but the difference in total temperatures between at the turbine inlet and the compressor outlet. So, that is T03 minus T02, and the air inlet temperature is nothing but your compressor delivery pressure. So, based on this you can fix this point, and accordingly you can drop a vertical. So, it will cut the fuel air ratio axis. So, when you do this, then you can calculate the graphically the fuel air ratio. This is a common approach which is followed in the gas turbine engines. The other term that is also important is nothing but the combustion intensity. Now, if you want to compare two combustion chambers, then another way of quantification is that combustion intensity, that is Ci is equal to Qr divided by Vc into P in, where Qr is the heat release rate, Vc is the volume of the combustion chamber, and P is your inlet pressure. So, combustion intensity you can calculate. This is in this way people have used that, which in this way what has been done is that Vc times P in, that becomes an additional parameter to compare two combustion chambers. And some numbers, realistic numbers of this combustion intensity is about 2 kilowatt per meter square atmosphere for aircraft engines, and 0.2 kilowatt meter square atmosphere it is used as a for aircraft industrial plant. And another last point that I want to mention here, that when you talk about gas turbine engines, what are the fuel that are used? So, for aircraft gas turbines, we use light petroleum distillates, and typically they are nothing but the high grade kerosene, whereas for conventional gas turbine power generation, people use natural gas. And if you look at their calorific value, gross calorific value, high grade kerosene has about 46.7 megajoule per kg, whereas for natural gas it is about 42.4 megajoule per kg. So, with this I conclude this gas turbine aircraft propulsion topic, and lastly I will touch upon another problem, that is again on the turbojet engines, and similar problem was solved in our last lecture, but still I stick to this fact that solving these problems will help a complete understanding of aircraft engines. So, let me start this particular numerical problems. So, it is a turbojet engines which is flying at 220 meter per seconds, and it is an altitude conditions where it is 0.24 bar and minus 50 degree centigrades. In fact, we know the compression ratio, the maximum cycle temperature, that is turbine inlet temperatures, and But for this type of problems, typical analysis or calculation what requirement would be calculation of thrust and specific fuel consumptions. Other additional data you require about isentropic efficiency, that is for intake, compressor, turbine and propelling nozzle. Also you require mechanical and combustion efficiency, combustion pressure loss and nozzle outlet area, and this nozzle outlet area is required for thrust calculations. So, let us solve this problem. Now, to solve this problem, first thing that you do is that draw the this cycle diagram. So, cycle diagram can be drawn like this, and it is nothing but your TS diagram. So, in the TS diagram we have to draw first intake process, then we have to draw this compression process, then we have to draw the turbine process, and in the turbine there is a drop in pressure, and finally the so this straight line will be actual process, isentropic process, dotted line will be actual process. So, if I know this location, I can put this number as A, 1S, 1. So, 1 to A is intake, 1 to 2 is compression, 2S is isentropic compression, 2 to 3 is the turbine, 2 to 3 is the heat addition in the combustion chamber, 3 to 4S is your isentropic expansion, 3 to 4 is actual expansion, 4 to 5S is your expansion in the isentropic expansion in the nozzle, 4 to 5 is the actual expansion. Of course, and if you can draw this as constant pressure line which is ambient, PA and TA. These values are already known as 0.24 bar and minus 50 degree centigrades. So, when you start the solutions, first thing that we have to find out the kinetic energy, that is half Ca square, and you know that Ca as, if you Ca as 220 meter per second. So, kinetic energy can be calculated as 24200 joule per kg. This kinetic is nothing but we can write as Cp times T01 minus Ta, and that is 24200, and here you have Ta as minus 50 degree centigrade. So, it is 223 Kelvin, and from this, and we also have Cp is nothing but 1.005 kilojoule per kg Kelvin. So, this will give you T01. So, T01 we can find out 247. Okay. So, we will take as intake, that is intake efficiency, we can start writing as T01S minus Ta divided by T01 minus Ta. So, from this we know Ta, and that intake efficiency is 0.9. So, from this we can calculate as T01S minus Ta as, we know T01, we know T0A, we have efficiency 0.9. So from this we can directly calculate as this number T naught 1s is 476 Kelvin. So once you now know the P naught T naught 1s, then you also require P naught 1. So for that we can write P naught 1 by PA is equal to T naught 1s by T naught TA to the power gamma by gamma minus 1. So we say gamma is equal to 1.4, TA is known, PA is known, PA is 0.24 bar, TA is known as 23 Kelvin. So gamma also is 1.4. So this will give you P naught 1. So P naught 1 is 0.3317 bar. Then we have to look into compressor. So for compressor we know P naught 2 by P naught 1 as 10. So this will tell you that T naught 2 S by T naught 1 to the power that is equal to P naught 2 by P naught 1 to the power gamma minus 1 by gamma. So we know P naught 2 by P naught 1, we know T naught 1. So this will give you T naught 2 S as 476 Kelvin. So further this compressor efficiency, that is eta C, is nothing but T naught 2s minus T naught 1 divided by T naught 2 minus T naught 1, that is nothing but 0.9. So this will imply that T naught 2 minus T naught 1 is equal to 256, and from this we say T naught 2 would be 503 Kelvin because T naught 1 is known. So we have this compressor. Then we will move to turbine. So for turbine we start with this equation. What is P naught 3? P naught 3 is nothing but P naught 2 minus delta P in the combustion chamber. This is 0.15 bar. So P naught 2 is already calculated, 3.317 minus 0.15. So it is 3.167 bar. And also turbine work is CPG times T naught 3 minus T naught 4, and that is nothing but compressor work divided by 0.98 by involving mechanical efficiency as 0.98, and this compressor work can be written as CPA, that is T naught 2 minus T naught 1 divided by 0.98. So we all have known that we have CPA 1.005 kilojoule per kg and CPG is 1.148 kilojoule per kg Kelvin. So we have CPG, we have CPA, we have this difference. Then T naught 3 is given as 800 degree centigrade. 1073 Kelvin. By solving this, we can get back this number T04 as 844.3 Kelvin. Further, and also we require T4s, so we can rewrite this turbine work as again by incorporating turbine efficiency as T03 minus T04 divided by T03 minus T04s, and from that is nothing but turbine is 0.92, and from this equation we know T03, we know T04, okay, and we require T04s. So this will give you T04s as 824.4 Kelvin. So we get the isentropic temperature expansion in the turbine, and again once you know this, we can calculate P03 by P04 as T03 by T04 S to the power gamma by gamma minus 1. Here gamma in the turbine is 1.33 and T04S is known, T03 is 800 degree centigrades. We also calculated P03, so this will give you P04 as 1.095 bar. So once we know this P04, so we can calculate P04 by PA, and this is nothing but NPR, nozzle pressure ratio, and this number we can find out as PA is 0.24, so 1.095 divided by 0.24, that is 4.55. And if you look at this nozzle pressure ratio, this will take you that we get a choking flow, because this pressure ratio is very high. And for this region again we can say for choking condition of nozzle, we have to calculate choking condition for nozzle. So choking condition calculation for nozzle, we say we have to define as critical pressure Pc by P04 is twice by gamma plus 1 by gamma minus 1. So this number is 0.54, and Tc by T04 we can calculate twice by gamma plus 1, that is twice by 2.33. Okay. Now we know P04, we not know T04. So this will give you Pc, or that is critical pressure, that is nothing but P5, that is exhaust from the nozzle, 0.5913 bar, and Tc, which is nothing but T5, that happens to be 725 Kelvin. So basically condition 5 is now known, and if you see this pressure and temperature is much high than this, so it is, so this whatever assumption you have said that choking condition is nozzle, so that is taken care by looking at ambient pressure values and this critical pressure value from the nozzle. Then we have to take the calculation for nozzle or jet pipe, that is 0.92. So efficiency you can rewrite as T04 minus T5 divided by T04 minus T5s, and that is nothing but 0.92. So we know T04, we know T5, okay. So this will give you T5 phase, and this T0 5 phase as 714.3 Kelvin. So once we have this, then we can calculate P04 by P5 is equal to T04 by T05 phase to the power gamma by gamma minus 1. So again we have gamma 1.33, we know T04, we have T05 phase, we know P04, so this will give you P5 as 0.558 bar. So we have P5, we have T5, so sorry, this is P5 critical pressure, so we can get P5. Now we can take rho 5 as P5 by R T5, that is density. So R is for combustible gases is again 287 joule per kg Kelvin. So T5 is known, P5 is known, so this will give you rho 5 as 0.268 meter cube per kg, and C5 is square root of gamma R T5. So gamma is again 1.3, R is known, T5 is known. So C5, that is jet velocity that comes out, is 526 meter per second. So from this we can say what is the mass flow rate of air, that is rho 5 A5 C5, and all numbers we know, this is about 11.28 kg per second. Okay. And last segment that we are going to calculate is about specific thrust. So here there are two parts, one is momentum thrust, so this momentum thrust is m dot Cj minus Ca, and we know Cj, that is 11.28, is the mass flow rate, jet velocity is already find out 528, Ca is 220, and this number is 3362 Newton. Pressure thrust, nothing but P5 minus PA into A, and we know P5, that is 0.558 minus 0.24 into area is already given 0.08. So this is 2544 Newton. So total thrust now becomes addition of these two, it is 5906 Newton. So we get then heat supplied, Q is m dot Cpg into T03 minus T02. So previously we have calculated m dot as 11.28, Cpg is 1.148, that is for gas, combustible gases. T03 already calculated, that is T03 is already turbine maximum temperature, that is 1073 Kelvin, minus T02 compressor outlet pressure 503. So this value turns out to be 7382 kilojoule per second, and this Q we can write as mf, that is mf QCV into combustion efficiency is equal to Q, and we know this combustion efficiency as 0.98. So, from this, that is your Q. So, Q is known here. So, from this equation and QCV here you can make an assumption that the calorific value, that is 43.3 megajoule per kg, that is 43,300 kilojoule per kg. So, we know QCV, we know combustion efficiency, we know Q. So, this will give mass flow rate of the fuel, m dot f, that is 0.174 kg per second. Now, we have got this mass flow rate, then we can calculate. So, first thing we calculate thrust developed, which is this. Second part is specific fuel consumption, SFC. SFC is equal to mf, m dot f divided by thrust, that is 0.174 by 5906. So, it is in kg per second. So, I have to multiply it 3600. So, this will give you a value 0.105 kg per hour Newton. So, after a long process, at the end of the day, we only require this thrust and specific fuel consumptions, and this simple turbojet engines gives you the entire concept, now how entire process has to be followed. Okay. With this, I conclude the lecture for the today, and module 4 is completed, that is gas turbine is completed. Thank you for your attention. We will see you in the next module, that is on refrigeration and air conditioning. Thank you for your attention once again.